the problems that we're going to talk about today, the program, the code that we're going to write, it's going to be about just a binary classification, just to stay simple. But I will also explain, how support vector machines can be applied on more than two classes, just not only just binary classes, but more than two classes. When it is binary classes and the scenario, suppose we assume that the scenario is simple, that we can just draw a line between the two classes and we can distinguish between the two. It's just like when the data is linearly separable, meaning we can just simply draw a line between two classes and have one class on one side of the line and another class on the other side of the line. That's when we have just a simple linearly separable, data that we can draw the maximum margin separator and then just simply increase the margin and keep increasing the margin until we hit, the support vectors. Support vectors are actually the data points that are the furthest from the maximum margin separator that can allow us to just simply expand this region. And support vector machines actually become an optimizer, optimization algorithm by optimizing this region, or meaning maximizing this region given us some subject to some constraints. And the constraint was 2 divided by the W. W basically is the region, this region. Okay, Ronald. Yeah, these are the closest vectors to the region that we have. So we have to keep maximizing it until we hit the first region of each instance, each class. Until we hit the first data point, first support vector. So we keep increasing this region. So we start with this, we draw a line, and this line can be in this way or in any direction, right? So we have to keep maximizing this region and keep fixing this line until we hit the support vectors. So if it was, let's say, something like this, then maybe W was probably larger than this compared to this. So we have to fix the line to the orientation of the line and keep increasing the region until we hit basically the first instance of each. It might be possible that there are multiple support vectors that hit this region. That's okay. Okay. So support vector machine keeps the information about these extreme examples. If you remember, I gave a very simple example about the extreme data points, which is why support vector machines are known as, rebellious, very resistant algorithms, and very robust when we have small data sets. Okay, because it is kind of a hybrid algorithm. I wish I had time to explain what parametric algorithm is and what non-parametric algorithm, but this is not the point. Sorry, parametric and non-parametric, but so it's not the point. It actually should be part of the machine learning lecture. Okay, so here support vector machine can either draw a line and have a linear kernel. So there is a kernel trick in support vector machines. Okay, that actually it uses either a linear kernel or some other sort of kernel, something like this. Suppose that if we had the data that looks like this. No, when this data set is small. So these are known as rebellious algorithms because all what it has to remember is those extreme examples. About these data points, it just doesn't need to worry too much about it because they're further from the region, from the line. Okay. So it has to remember those extremes. So these are the extreme examples because these are very difficult to detect because they have more similarity to each other. Okay. Which is why support vector machines are known as, rebellious algorithms. Suppose that we had data that looks something like this. Maybe here too. Can we draw a line? Yes, we can. But the problem is if we draw the line, in this case scenario, we are misclassifying 3 data points there. If we draw a line, if we are using the linear kernel in support vector machine, we are misclassifying 3 data points, right? Support vector machine has a trick, a kernel trick. It doesn't have to be just the linear kernel. because right now we are only drawing it in, 2 dimensions. We can use either a Gaussian kernel or it's called radial base function. What you can do is you can draw a region something like this. Okay, it will draw the region based on the probability distribution of the data when the data is basically not linearly separable. So you can also do nonlinear classification too, using support vector machines, and we will see what those different kernels are that support vector machines can use. This is going to be one part of the exercise that we're going to do today. As if you remember, we have the model development pipeline, and we will go over the pipeline, and I'll show you guys why it is very important to do the data visualization and data preprocessing in order to improve your model. Ronald. In a mathematical sense, this kernel is not actually the one that we covered in operating system. That operating system, that kernel is different. In that sense, it's the operating system itself. Here, it's a different thing. I will explain that in a few minutes. Okay. Next, we have decision trees. What decision tree does is basically as its name suggests. So it continues, it iteratively creates the splits between the data until all the data is classified into, each classes. Something like this. Now, suppose you see that, you look at this data and say, maybe, one split, if we do this split probably, or maybe split number 1, something like this. Okay, we can have this split, and we can say if x1, so suppose that this is x1, this is x2. If it is, let's say this is value from 0 to 100, right? We can say, oh, you know what? If x1 is less than 50, and let's make another split number 1, and then split number 2. And I say, if x1 is less than 50, and x2, let's say this is 70, from 0 to 100, and x2 is greater than 70, then the class is always plus. All the data points are, assigned to class 1. Else, otherwise, it's class, I would say red. I should have done this plus or minus, right? So we can perform multiple splits, and then next time we can say, all right, we can create another split number 3, and split number 4. And I can say, well, this is 65. If x1 is greater than 65, and s2 is greater than, let's say, 25 and less than 70, then the class is always green. So we continuously do the splits in the data. So right now, this is just only 2-dimensional. Okay, so decision tree continuously splits that data into appropriate classes, and that's based on the concept called information gain, which depends on the entropy. Entropy has a formula, I, probability of I times minus time log of probability I. So the parameter or the attribute that we have that has the smallest entropy is going to be selected for the split. And after every split is actually a bunch of if-else conditions in a decision tree. So we start at the root and say, we're going to pick like one of the parameters and say, if the value of this parameter is less than a certain value, okay, then just go for the 2 branches. And then in the next branch, if the value of the other parameter that is going to be chosen, okay, at the next branch, that is going to be chosen, if it is greater than or less than some value that it actually finds out based on the entropy of each attribute, then just do further splits. And it goes all the way down at the tree where there are leaf nodes that actually make the decision, where no further split can be made. Something like this. Now, suppose, let's take the same example and say, all right, if x2 is greater than 60, what happens? So let's say x2 is the vertical bar, the second x1 and x2. Suppose that we have two attributes. And suppose that this is the value 60. If x2 is greater than 60, then what happens? All right, we have performed one split. If x2 is greater than 50 and x1 is less than 50, then it's always the green class. I'm actually doing this classification. Okay. Otherwise, it's these data points. These data points, they're always red, right? What happens if x2 is less than 60? Okay. If x2 is less than 60, then if x1 is less than 70, somewhere here. If x1 is less than 70, then I'm having these data points. They are once again all in the red class. So I'm actually performing the splits and I'm creating a decision tree. Okay. So a question in your homework might be, here's the data set. Here are the two parameters, or maybe three, maybe just two in 2 dimensions. Perform the splits and create a decision. Really simple. Okay. So your splits, you may start with x1 instead of x2. That's okay. Okay. So that's actually the trick that is played by the decision trees that actually tells you how to perform the splits and how to create a decision tree. Okay. So I'm gonna start with our what is the purpose? X1, X2 can be the parameters in your data set. Something like, I talked about. No, X1. So like this is the first parameter and X2 is the second parameter that you have. X1 can be your age. X2 can be your height. And then you're saying that if your height is, let's say something, greater than, let's say not just from 0 to 100, but based on your age is like, let's say from 20 to 100, something like that. And then your height is from, let's say 4 feet or 3 feet to, or 0 feet. Well, nobody is of 0 feet. From, let's say 2 feet to 7 feet. Okay. So these can be the real parameters in your data set. We will talk about that in just a few minutes. Nathan. Yes, true. 12, and then I'm going to this. All right. So I'm going to get back to our coding programming exercise. So that everything makes sense about what we are going to program today. All right. We've talked about supervised learning, but using by support vector machine and decision trees, because we were seeing that all the data points were labeled. We were saying that, which ones are of green class and which ones are of red class, right? So we knew the classes. There are some scenarios in which you don't even have the class information. What you can do is, as a first step, you can cluster some data or you can perform some unsupervised learning algorithm to come up with a preliminary classification or preliminary clustering. And based on that, then you design a machine learning model. In order to do that, I'm going to go over just only one of the very famous algorithms, that is k-means clustering. Let let me stop this so that I know where I have to draw. All right. What k-mean? How many of you have even heard of k-means or clustering? K-means. Okay, 2. So I'm gonna go over very quickly what k-means is. Okay, in terms of the just a theoretical description of k-means. So suppose that you have data points like this. Now, the reason why I drew all of them in red, because right now we just don't know any information about the classification of data points, okay? Suppose that we again have x1 and x2. What k-means does is it just has 5 very simple steps, and it clusters the data, or it classifies the data according to, based on different clusters. So you can either tell k-means how many number of clusters or how many different number of classes that you want to classify each data point into, or the k-means also has another trick or the way to automatically find out how many different number of classes to be created, how many different number of clusters can be created. It is actually called the elbow method. The elbow method is, it actually starts with random number of clusters, increases from 1 cluster to 2 to 3, 4, 5, 6, 7, 8, and so on and so forth, and then sees what is the number of clusters for which the intra and inter-cluster variance is the lowest. Okay, is the lowest. So we will talk about that, but if we have time. So right now, what we can say in a very simple case scenario, we say that, okay, we want the algorithm to perform, let's say, 3 clusters. So we first of all, we choose how many number of clusters that you want to create. Okay, how many number of clusters. Second step, you actually draw random means or random numbers. So random numbers, that how many number of random numbers? A k number of random numbers. Okay, random means. So what you do is, what k means does is it actually draws random means based on random number generator, something like this. Okay, it draws some, like random numbers, and then the third step is the most important step, is actually it calculates the distance, which is, let's say, Euclidean in our case, distance for each mean to each data point. What I'm saying is that this mean is going to have a distance calculated from every single data point that we have. It's an iterative algorithm, by the way. This one also is going to have a distance between each data point, and then this one too. After one iteration, okay, what it does is, so let me just take this off, erase it. Okay, after that, update, basically, I'm gonna say cluster each data point based on minimum distance from each mean. Meaning, what I'm saying is that it's going to look at each data point and then see which mean is this data point the closest. Something like this. So this is this one, this one, this one, probably this one. All these are closest to this one. So it actually is going to cluster these data points according to cluster 1. Let's say this was mean 1, this was mean 2, this was mean 3. So it's gonna maybe this data point actually is closer to this. So this is the first iteration. Something like this. Then it is going to simply update the means based on these clusters that are created, it's going to start moving the mean closer and closer, and bringing the average, bringing the mean closer, basically at the center point of each cluster. Okay, so that's one iteration. Then it's going to do another iteration. So it iteratively updates the means to a point when there is no change in the means anymore. And then finally, it actually creates the clusters, something like this. And by that point, it is hoped that these means actually move right at the center of each cluster, from here to here, from here to here, and from here to here. That's it. That's k-means clustering. Okay. So let's just stop and let's go to our programming exercise. And our programming exercise is going to be based on the example that I have included. This example. All right. We are going to assume that each of you actually is working as a software engineer or a data scientist at a company, at a really cool company that is maybe a car dealer, something like that. Okay. And you're really interested in selling this new SUV that has been manufactured, and you're basically, given a job to, increase the revenue and become one of the most important player in the company and most important individual. So you're working as a data scientist. Your manager comes to your desk and says, look, we have this SUV. It's a really cool car. We're actually trying to sell it. And we're trying to basically increase our revenue. What happens is your manager comes to you with a piece of paper, with a sheet, and says, like, look, I've actually looked at different social media, platforms, and I have gathered or collected some data about some people who have or may have not purchased this specific SUV based on their age and their annual salary. So your manager comes to you and says, like, I have about, let's say, 400 people, all right, that I have collected information about from different social media, let's say Twitter, Facebook, et cetera, and I say, each person, I know the age of each person, and I know the annual salary of each person, and I also know from those social media, websites, that whether or not they have purchased this SUV. Okay, so based on the annual salary and the age, we may have different more parameters too, but let's just keep it very simple, a three-dimensional problem. Okay, why it is a three-dimensional problem? Because we have two input parameters, customer's age and estimated salary, x1, x2. These are the independent variables, or the predictors. Okay, these are the two dimensions. And then we have our dependent variable. We're going to say, if we know the customer's age and estimated salary, we know whether or not they purchased this SUV. So our purchased can be purchased either yes or no, or 1 or 0. We can call it a binary classification problem, right? Like 0 means a customer of a specific age with specific annual salary, they just did not purchase this SUV. And some customers with a specific age, given specific age and annual salary, they have purchased. So it's a binary classification problem. So now your job is to develop a machine learning model based on your manager's request, asking you to design something for a data-driven approach for the company, so that if a new customer arrives, new potential customer that you may or may not know as a company, and you're just going to predict if they are going to buy that SUV or not. Because if you know this information, this can be very important for the company. Because if you say that if the customer is not going to purchase that SUV, you can build a recommendation system and say, you can say some really nice things about SUV and say it's going to save you money and it's really good about mileage, blah, 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 blah. You can build it. Yeah, like with SUV or with any car. It's just an example. Yeah, may not make sense. Maybe something else. Okay, maybe something else. All right. So maybe it's electric. So maybe the idea is actually to build a recommendation system. So you're going to design a machine learning model. And remember, I told you the model development pipeline. Almost every single project that I have done based on machine learning or data-driven approaches, I've always followed this approach, because this is also whatever number of people I have interviewed and recruited for jobs like this, the job description almost always mentions this flow or the sequence of steps that you have to do to create a machine learning model. So what we are going to do is we're going to import, basically, if you remember, data collection, data pre-processing, exploratory data analysis, model development, model evaluation, and then model hyperparameter tuning. Those steps. These ones. Okay, just remember these. We're going to follow for all projects that we are going to do or homework activities that we're going to do for the rest of this course. Is actually going to be based on these steps. Okay, so remember that, because this is going to be very important. So data collection. All right, we have the data. Suppose that the manager comes to us and gives us an Excel sheet or a piece of paper, right? So we have the data in hand. So now we're going to actually require some libraries. Suppose that we are Python developers also. So we're going to write code in Python. Okay, we're going to continue writing code in Python in this course. So we're going to import some required libraries. Then we are going to load the data set, okay, that we're going to have. So for some required libraries, what we're going to use is we're going to use NumPy, and we are going to call it NP, to actually work with vectors and matrices. This is a very useful library to work with matrices and some vectors. We're also going to plot something. Because remember, one part of the pipeline is visualization of the data. Okay, so we're going to use something called matplotlib.pyplot, and we're just going to call it PLT. And finally, to deal with opening, reading from, writing to, and closing the Excel sheets, or the CSV files, we're going to use this library called pandas. It's really good. So for now, let's just use built-in libraries. Okay. In your machine learning course, you might be asked to actually design your own code to read and write and not use too many libraries, because that's the purpose. You need to understand the technical aspects of machine learning. Here, we're going to talk about artificial intelligence, how some approaches can be applied. So for now, we're just going to use some built-in libraries. Okay, so we're going to use scikit-learn, or in short, it's called sklearn. We're going to use multiple libraries from there, already built-in approaches like support vector machines, decision trees, et cetera, et cetera. These are all part of this, tool that we have in Python. All right, we're going to load the data set. Then remember, we're going to say that for model development, we're going to do the train test split. We're going to actually evaluate the model, how good the model is that we have developed. So what we're going to do is we're going to use some amount of data to develop the model by showing it the class, by showing it that if you see a data of this sort of format, then it belongs to a certain class. So once it is done, once it remembers or once it learns about the patterns within the data, we're going to use the rest or the remaining portion of the data to test how good it is. That data is basically never seen by the model. Okay, so what we're going to do is, suppose that we have the data set. We're going to draw, let's say, 80-20, or maybe 75-25% split. Nathan. Not for very specific for this programming activity, but for next week, we're going to do cross-validation. Okay, so what we're going to do is, in training data set, this is going to be our training data set. in which we are going to have the X, the input parameters like the age and annual salary, X1, X2. And we are also going to tell the model what each instance belongs to. So our instance, our output is purchased or not purchased, right? So we're going to train our model based on both the input parameters as well as the output parameters, X and Y. And then for the test data set, we are only going to give our model the X, the input, and then we are going to ask the model to predict the Y for us, to predict whether or not this customer of this specific attributes is going to purchase the SUV or not. So that's going to be called Y hat. And then finally, we are going to evaluate the model by looking at the actual values, because we now have the Y values for that, because we saved that data for the later purpose. And we're going to look at the output, actual output, and then we're going to simply compare it with Y hat. Okay, we're going to compare it and see how good basically the predictions are. And the predictions that we are going to compare with the actual output is going to be based on accuracy score and confusion matrix. I'm going to tell you guys what confusion matrix is. Some of you may already know what a confusion matrix is, but in simple, confusion matrix is the true positive versus predicted positive and true positive versus predicted negative, false positives. Okay, I'm going to talk about that in just a few minutes, what confusion matrix is. All right, great. Then finally, not finally, after the train and test data split, we're going to pre-process it. Remember, we said that one attribute might be within the range of, let's say, 0 to 50, and then another attribute might be 0 to 100,000, something like that. So we want to make it easier for the machine learning algorithm to do the computations more efficiently and more effectively. So we just either normalize the data, right? Normalize, or standardize the data. Normalization simply converts each column or each data, each attribute within the range of 0 and 1 with that formula that we covered on Monday. Standardization is also good because it standardizes the data based on a mean value. Let's say we have a mean value 0 in this case. Because we're going to use a model that actually is going to draw a distribution of the data instead of just normalization, we're going to use a standardizer instead of a normalizer here. So the data or the model that involves like a probability distribution, it's better to use standardization instead of normalization. Okay, but there's no definitive answer between the normalization and standardization. So all what we're going to do is we're going to have the data distribution. We're going to transform it to another dimension where it has a distribution given a mean value. A mean value can be anything, not 0. But we're going to just for this specific purpose, we're going to standardize our data according to the mean value, which is 0 in this case. All right, we have done the data pre-processing. There is a reason why you have to do the data pre-processing after the train and test split. Some of you might say, well, why didn't you just, pre-process the data before you even did the train and test split? There is a very specific purpose for doing the pre-processing after the train test split. One of the very important, most important, by the way, I'm going to share a document with all of you guys about, I think, 5 or 6 novice mistakes that new machine learning developers make, for designing a data-driven approach. And this mistake, what people do is that they do pre-processing before the train and test split. It is actually one of those very silly mistakes that people do. Why we have to do the pre-processing after train test split? Because suppose if we were to standardize the data before the split, then you're actually leaking information from the training set to the test set. You're actually telling the information that I'm going to draw a distribution. But when the model is developed, you're secretly whispering in the ear of your machine learning model that your test set is also going to follow the same distribution, that you can't do it because then you're being biased about the data, which is why you have to do the pre-processing after the train and test split, because you really don't want your machine learning model to know anything about the tested data set. Run it. Training set that we use to develop the model, in which we tell the model that we have input parameters, and we also tell it the class, what class. You know, we train, we give it the examples that are labeled. So we teach, just like how we teach as, you know, a kid about the difference between a cup and a glass by showing them several examples, and then we're showing the kid saying like, you know, this is the cup, this is the glass, and you bring multiple different colors and different shades of glasses and cups, and then you're teaching basically the kid. And once you think that the kid is trained, a child is trained, you just actually bring an unseen, you know, glass or a cup and say, what is this? Is it a cup or is it a glass? Okay, so that's the training set where you tell the model, you teach the model. Then we do the model development. We're gonna use support vector machine here and decision tree, all right? And finally, we do the accuracy test, and we are going to evaluate the model and visualize the model. I'm gonna stop. Can someone take the screenshot, because the code that I'm going to write are actually going to be based on exactly these steps. So if I forget, so that we don't lose or, you know, waste time by coming back and forth to this slide. Okay, so I'm gonna start writing the code. If I make any mistake, you are more than welcome to correct me, okay? So now, another important thing that you will have to remember is that while we are writing this code, please pretend that you are a very cool, highly paid data scientist at a cool company. All right, so what I'm gonna do is I'm going to move this window over. By the way, I still use Anaconda, and it is extremely small. Screen resolution. Let's say if I view screen resolution. Let me just do, well, okay, this is not bad, right? So before I start coding, I'm going to select the environment in which I already have all the, you know, libraries installed, which is TensorFlow. I just called the environment TensorFlow GPU. I'm going to select that, and once I have selected it, I'm not gonna update it. I'm going to launch Spider. Okay. All right. So this and all right. So what is it? Oh, that's the real ant that I was working on. I'm going to go over data. Yes, USB. Teaching is info. I'm going to select this folder. I'm going to go and where is my support vector machine? Oh, no. This one. All right. So I left some code to visualize the data because I will show you once I get to that point why I just left this code, because it would have taken a lot more time to write these lines. So I just left them. But according to the sequence of steps that we have talked about, we're going to start coding. Okay. So I'm gonna call it implementation of support vector machine for classification. So what was the first step? Importing some required libraries, right? So I'm gonna import, is it writing something? Yes. Import NumPy as NP. Okay, I said we're gonna import some libraries. What was the other thing? Import matplotlib lib.pyplot as PLT. All right. Then finally, I'm going to import pandas as PD. Sounds good? Scikit? Yeah, it might be a good idea. So I'll do that when we get to that step. Okay, so I'll do that like one by one so that people understand. That's a good point. Okay, scikit-learn, which I just explained in one of the slides, that we're going to use scikit-learn that already has built-in models, support vector machines and decision trees. The reason why we are going to use the built-in models because we are not going to explain in detail what the math behind support vector machines and decision trees are. Okay, so we have it. Ignore the warning signs because it's what it's saying is if you move the mouse over, it's going to say it's imported, but it's not used yet. So we're going to talk about that soon. All right. What was the next step, by the way? Load the, sorry. Oh, NumPy is misspelled. Oh yeah, good catch. There you go. NumPy, this one. All right, the next part is load the data set, right? We're gonna simply load the data set. I'm gonna call it the data set, and all what we will have to do is from pandas, we're going to use this function read CSV. And all what we will have to do is we will have to give it this path file name that we're going to use. Here, we're going to use social network ads. So I'm going to say social network ads dot CSV. I'm not going to give it a full path because it's exactly the same directory. So if I look at what this is, remember, we have X1 as age, X2 as estimated salary in thousands, and then we have purchased or not purchased. 0 means this customer, specifically this customer who was pretty young, 19 years old, and they had only $19,000 as an annual salary, they did not purchase this vehicle. Someone who was of the age 32 and had about $150,000 annual salary, they actually purchased. Okay, so these are, remember I said that we have about 400 customers. So our manager has information about the 400 customers and what they want us to develop or design a machine learning or data-driven approach to actually train the model on the data that we have and then predict for a specific, for a person with a specific age and salary, predict whether or not they're going to purchase. So our input parameters are going to be this, and our output is going to be purchased. Sounds good? And we have 400 data points. All right. So this, using this, we already have the data set loaded. So what we have to do is, basically, we have to split the input variables from the output variable, right? Because remember, we said that when we do the train and test, for train, we're going to use both X and Y, but for test, we're only going to use the X input variables. So it's better to just split them, separate them. So what we're going to do is, I'm going to call the X, the input parameters. I'm going to use a function called ilog, locations. I'm going to select all rows, all 400 rows, and every column except the last column. So that column -1 means the last column. Last column is purchased. So my input parameter, my input is just going to be in X now. And I'm going to use Y as dataset.ilog, all the rows and only the last column. minus 1. So I didn't use colon minus 1. Make sense? So for X, all the columns except the last column, and for Y, only the last column. So this colon minus 1 does a really good trick in this function ilog that selects all the columns except the last, and then without the colon, it just selects the last column. Okay, so let me try to run and see if the code works. NumPy. Oh, when I double clicked it, yeah, okay. So, okay, worked, which is good. Did this work? Okay, no error, which is good, which is great so far. Next, what was the step, by the way, next step? Split data set into, I'm going to have some typos in the text, okay, into train test splits. Okay, what we're gonna do in this is we're gonna use a built-in library that is going to be called, so if we go to sklearn website, scikit-learn and API, and if we search for this train test split, we're simply just going to use train test split. That actually does the random split between the train, random split for a data set, and it just gives us the split between the split of that data set into train and test. It's a built-in function that we're going to use. So back to James's suggestion is that we should just do it here. So from sklearn and model selection, we're going to import train test split. Sounds good? All right. So all what we're going to do is it gives us actually returns four objects: X train, X test, Y train, and Y test. And then we're simply going to use the train test split. And we're going to use X, we're going to use Y, and we're going to use a 25% split. Meaning we're going to use 75% of the data as train and 25% of the data as test. Okay, so, and then here is another, I think, random state equals 0. So random state is this. Let me tell you. So it takes the input X and Y, train and test, and it splits the data based on the split test size that we give. And random state is going to be this. So because it randomly distributes the data, if I use train test split on my computer, it will randomly, train and split the data. And if you're going to use, suppose that if you want to run the code or program on your computers and want to see exactly the same results that I get, you will have to set a random seed that has to match. So when I set the random seed to a number here, if the number matches on another computer also, then the computer is going to generate the exact same random split as what I did here. So in order to see the same results, we're just going to use random state in here. Okay, random state, which is 0. Okay, so if I say when I ran this code, I should actually have X, which is 400, and to age, and remember, an estimated salary. This is the input, and this is the output. So all what it did is it just took the data from the from the Excel and created X and Y. All right, that's great. So once I run this code and it says train test split is not defined. Train test split is not defined. Oh, because we haven't called this yet. So every time we import new library, we will have to call this because I'm actually defining it right above. Okay. So it has created X train and X test, Y train and Y test. What is the 25% of 400? 100. So you see here in X train, it's split the data 300 samples into X train and 300 samples into Y train. And then for X test, it has set 100 samples. Okay. What was the next step, by the way? Standardize, right? Standardize. Okay. We're going to use once again a standard. We're going to use a standard scaler, by the way, a built-in function from sklearn once again. All what it will do is it will just standardize our data with respect to a specific mean value, actually 0 in this case. So all what we will have to do is, in order to avoid errors, I'm just going to import right here so that when I run this section, I'm not going to have to just run the top section once again. From sklearn pre-processing, I'm just going to import standard scaler. I'll have to create an object of this, which is sc equals standard scaler, and great. We are ready to use standard scaler. Okay, so we're gonna use the standard scaler on X train and X test because we really don't need to do scalar standardization on train on Y, on the predicted variable on the predictor variable, because it's already 0 or 1. We really don't need to do any standardization on that, right? So I'm going to use X train equals SC, and it's called fit underscore transform. Fit transform. I'm going to use X train. I really don't need to do other parameters at this moment. All what I will have to do is just simply scale that or standardize my X train. And I'm just going to have to do the same for X test, X underscore test. That is it. So if we run this portion, you see X train, if we go now, it actually, the data has been standardized according to a mean value. It's not, an actual age and the actual salary anymore. So we have scaled the data. Okay, great. What is the next step? Isn't it implement the model, right? So once again, we're going to use from support vector machine. By the way, support vector machine can be done, can be implemented for both classification as well as regression purpose. Right now, we're only going to use the classification because our output variable is classification, right? 0 or 1. So we're classifying. So I'm going to use this function called. So I'm going to import it. Import SVC from SVM. Okay, great. So I'm going to call my model classifier, and I'm going to say I am going to create basically an SVC, but with linear kernel. I'm just going to assume that my data basically is linearly separable, and I'm just going to use a linear kernel in this case. Suppose that we're going to use linear kernel for now, and then to generate exact same results on your machine, you just will have to set the random state to 0. Okay, so as soon as we are done with in creating the model, all what we will have to do is we do the classifier equals, classifiers dot fit. I'm going to provide it X train. I'm going to provide it the training data. Now I'm actually teaching the model, training the model, train, and I'm going to provide it the class information, right? X train and Y train. That is all. So all what we will have to do is create the model and then simply train it based on X train and Y train. So if I run this, hopefully there's no error. Oh, great. So we have actually trained the model. If you click on this, there is a lot of information that you can go over. This is actually, if we were in a machine learning course, we could have actually seen, or we could have gone through what are different parameters and what are different functions that have been trained by the support vector machine, and where are the mathematical details which created all of this. But because we're not from that course, we're not going to go over that part. One thing that we will have to go over is that it can actually use multiple different kernels, like linear kernel, polynomial kernel, RBF radial-based functions, sigmoidal, pre-computed, et cetera, et cetera. So right now, we're just going to use linear kernel, okay? So next, what is the next step? We're going to check the evaluation of the, so accuracy score, right? So we're going to import first confusion matrix. Where is confusion matrix? I'm going to use confusion matrix, okay, and accuracy score. So I will need confusion matrix, import confusion matrix, as well as accuracy score. What is the accuracy score? Okay, so what I'm going to do is first, I'm going to do this print classifier dot predict. Let's say someone with the age of 30 and has the salary of age of 30 and the salary of 87,000. And let's see what our model tells us. So if I do this, oh, they are going to buy. A customer with the age of 30 with 87,000 salary, they're going to buy it, purchase it, meaning the output one meanings, and they are going to purchase, right? And now what we will have to do is we're going to have to do the predictions for all the test data, right? Y underscore predict classifier dot predict X underscore test. That is it. For all the X underscore test, we're going to do the predictions and then simply just do the confusion matrix and accuracy scores. Oh, I actually messed up the steps. We'll have to do it here. All right. And finally, we're going to do print classifier dot confusion matrix CM. I'm going to call it confusion matrix. Confusion matrix, which is going to be the test, the comparison between Y test and Y predict. Okay. And then finally, the accuracy score is going to be equal to accuracy score Y underscore test and Y underscore predict. Let's try to run and see what happens. Oh, I didn't even do any printing. Print confusion matrix and then print accuracy score. All right, 88% accuracy, not bad. Should we try and see why it is at 88% accuracy and not close to 100%? Let's see. Now you see model tuning. Oh, okay. Okay, now there are some extra spaces that Python is not going to like. So if I do this and simply plot it, let's see how the data looks like. It's going to take a few seconds though. Give me 1 second, Rana. Okay, so right now it's running. Hopefully it's going to give us the 10:15. Okay. So we're actually the model evaluation. We're going to visualize some data and then see how the model worked and why it gave us 88% instead of, let's say, 95% or something. Okay. So as soon as it plots the data, I'm going to see what might be the issue that might have caused the accuracy to 88% instead of over 90%. Ronald, you were asking something? You can use tabs. So I think in tools and preferences, instead of spaces, you can use tabs as indentation, which is better. Come on, okay. It's taking a little while, but actually the idea would be, so while we do this, we're gonna use, we're just gonna go over and see what we can do for decision tree classification. So we're gonna use decision tree classifier for the classification model based on the decision tree. Oh, look, okay, so it has plotted some data, all right? So you see here, the data basically doesn't look very much like linearly separable, right? Because you see, when the model tried to separate the data based on a line, this bunch of data, this set of data, and this data was actually classified wrong by the model. So we can use a model support vector machine, which may have a kernel like this, right? Something like this. If we had a region like this, then all these classification instances could have been classified, better. So instead of using linear, we're going to use RBF kernel. Okay. So let's see what happens after that. So we're done with this part. We have learned the model. We did the accuracy. Look, by using RBF, we have gone over 93% accuracy from 88%. And if I plot this simply, just let's see how it looks like. And for decision tree, all what we will have to do is we'll have to import decision tree classifier. Okay, and I would say classifier equals decision tree classifier. Simply just do exactly the same thing that we did for support vector machine. Classifier dot fit x train and y train. That is it. By changing just the two lines, you have actually built a decision tree classifier. Python, yeah. So we are using matplotlib library, pyplot. So it actually gives us quite, good plotting visualization library. So I hope it just finishes quickly. I mean, you can use, I think I used red somewhere here. Instead of red, you can use black for first class. So you can change a little bit here in the plot part, and then you can use basically, so you see for 0, the classification basically points are red. For 1, the classification points are green. So hopefully this finishes soon. In the meantime, I will wrap up. and I will upload k-means clustering. Okay, because we didn't have time. I will upload the code for k-means cluster. So